This lecture is about acid-base titrations, and it is the second topic in chapter 16. So, quick overview of what a titration is. A titration starts with something called an analyte, which is typically a substance in which we don't know the concentration. And we're trying to figure out the concentration of it by use of something that's known, which we call the titrant. And so in this PowerPoint, we're going to talk about acid-base titrations. So clearly what the analyte will be is an unknown concentration in acid or base, and the titrant will be the opposite with a known concentration. So sometimes you need some way to signal that the titration is over, that the analyte has been completely neutralized, and that then you can do calculations to figure out what the concentration of it is. So sometimes in a titration, a substance is added, which is called an indicator, and the indicator changes color when you neutralize all the substance that you're titrating. In other times, you can use a pH meter and just look for it to reach a neutral or whatever pH you expect to be at the end of the titration. If a strong acid or a strong base is titrated, as you would expect, at the equivalence point, which is the point at which all the original acid or base that's being titrated is neutralized, at the equivalence point, the pH is 7. But what you will likely be surprised to hear is that when later on in the lecture, when we start talking about titrating weak acids or weak bases, the equivalence point pH will not be 7 anymore. So don't worry about that now, because we're going to talk about titrating strong acids and strong bases first. So let's imagine that we had a solution of hydrochloric acid and we didn't know its concentration. And so we decided to do a titration, let's say NaOH, and that has a known concentration. So we know the products from reaction of a strong acid and strong base. So at the equivalence point, right, all of the original acid that we're titrating is going to be gone, and all we're going to be left with is water and sodium chloride salt. And we have learned from the previous unit that sodium chloride is a salt that does not affect pH. And so, as we expected at the equivalence point, the overall pH after titrating a strong acid or strong base is 7. I also want to point out in this slide that what a titration curve looks like for a strong acid or strong base. So typically the volume of the titrant added is along the x-axis and pH is monitored along the y-axis, and the equivalence point is determined as the midpoint from this huge jump in pH. So you see right here where there's a big sudden jump in pH. That is the equivalence point. And so typically to find a more precise value for the equivalence point, tangent lines will typically be drawn on either end of the curve. The distance measured between those two tangent lines, and then the halfway point is the pH. How do you use the information that you've obtained from a titration to calculate the concentration of the unknown analyte? Well, it's basically stoichiometry. So you know the molarity of the titrant, right? The thing in the burette, substance in the burette, and you know how much of that substance you had to add to reach the equivalence point. So you know liters, volume, milliliters, whatever. And we have also learned that molarity times liters gives you moles of a substance. So we can pretty easily calculate the moles of the titrant that we added to reach the endpoint. And then keeping in mind from a balanced chemical equation of an acid-base reaction, assuming they are both just monoprotic acid and a base with only one hydroxide, that the stoichiometric mole ratio of the acid to the base was 1:1. So once we calculate the moles of the titrant needed to reach the equivalence point, we set that equal to the moles of the unknown acid. And then finding the molarity of the unknown acid is simply a matter of taking the moles that we just calculated and dividing by the volume, the liters or milliliters, of the acid that we titrated. And that is how we get the concentration of the unknown acid. So it'll probably make more sense when we work some examples. Here's a straightforward example. We have an unknown concentration of hydrochloric acid. Now this is commonly done, for example, we worry about the acid content in water, bodies of water, and so this might be a sample of stream water or lake water that is being monitored. But let's say that we have a solution of unknown concentration of acid and that we titrated it with sodium hydroxide. And of course, as always, the titrant, we know how much it took to reach the equivalence point and we know the molarity that we used. So what's the concentration of the unknown acid solution based on this information? So first step, as I went over the general directions on the last slide, is to find the moles of titrant used to reach the equivalence point. So that is simply the volume used times the concentration. And notice here, we could have used liters. So what you're used to seeing would be converting the milliliters to liters, right? And then multiplying that by the molarity. And that would have told us how many moles. So we would have got 0.003 moles of base used. You will notice in titrations, quite often chemists, just to save time, and also because the burette is marked off in milliliters, so it's easier, instead of converting the volume used to liters, they just keep it in milliliters. And so the unit you end up with millimoles instead of moles. Either way is fine, whatever you're comfortable with. And again, keeping track of the stoichiometry. So for every one NaOH that reacts, one HCl reacted. And so the number of moles we just calculated for the titrant base equals the same number of moles for the unknown concentration of acid. And then now, finding the concentration of that unknown acid is simply a matter of taking the moles we just calculated, divided by the volume that we started with, which the problem will have to tell you. Okay, started with 50 milliliters of that unknown concentration of acid. Notice what's kind of cool here. If you do work in millimoles and then you divide by milliliters, you're going to get molarity. So moles per liter gives you molarity, or millimoles per milliliter also gives you molarity. The millis cancel, right? So just save some time for you. Now that I've taken you through the step-by-step process, which really isn't complicated, to calculate the concentration of an unknown analyte, here's a shortcut for you. Here's the same question we just went over in the three-step process, and we're going to use a shortcut formula. This formula can only be used at the equivalence point of a titration. Now, as we get later on in this lecture, we are not going to go straight to the equivalence point of a titration. We're going to wonder what the pH is partway through the titration, and then we cannot, in that case, cannot use this shortcut, only for equivalence points. So make sure you make a note of that. Now, this looks very similar to the dilution formula we have used, which was M1V1 equals M2V2. All right, but there's a very important difference that I want to point out and I want you to make note of. You notice this little A in front of the left side and the B in front of the right side? That's critical. And that little A and B accounts for the fact that you can have a diprotic or triprotic acid, and you can have a base that has more than one OH. So let's say we are titrating with H2SO4. That has two acidic hydrogens. So A would be 2. If you were going to use this formula, you'd have to put a 2 there or you would get it wrong. The A and B is really accounting for the mole ratio in the reaction between the acid and base being titrated. So if you use a monoprotic acid with a base that only has one hydroxide and your mole ratio is 1 to 1, then of course it just drops to MAVA equals MBVB, and then it's just like dilution. But please be aware that won't always be the case. And you can see here by simply plugging into this formula, where M is molarity, V is volume. Again, your volume, just like in the dilution formula, your volume can be in either units of milliliters or liters. You don't have to convert it to liters because units is going to cancel out anyway. So plugging everything in, we get the exact same answer for the molarity of the unknown acid being titrated. So this tends to be an easier, quicker way to calculate information at the equivalence point. Now, as I said before, there will be occasions when you will be asked to calculate the pH of a titration at various points. You might be asked to calculate the pH of a solution before the equivalence point. Obviously, that can only be done if you know something about the analyte that you're titrating, right? If it's totally unknown, you're not going to be able to do anything with it. Then during the titration, you might be asked again, what is the pH halfway through? What is the pH 1/4 the way through? And so we're going to go through each of these regions. Then, of course, at the equivalence point is the point we've talked about already, where you can use this formula. And then in some cases, you'll be asked a question. Somebody will overshoot the equivalence point. In other words, if they're titrating with NaOH, for example, they may add too much NaOH, and so you may be asked, what is the pH if you overshot the equivalence point? So let's go through each of these scenarios. Yay. So, reading the question, we are calculating a known substance. This is just for practice doing these calculations, obviously. And the question is asking, what's the pH when we've added 25 milliliters? Now, just to get your intuition going in these titrations, notice that the concentration of the acid and base that are titrating are equivalent. All right, and then it's going to be a 1-to-1 stoichiometry. So it's pretty easy to see that we're at the halfway point here. Okay, that if we have 50 milliliters to titrate and they're at the same concentration, after adding 25 milliliters, we're going to have neutralized exactly half of the substance we're titrating. But let's go through the process that you go through when you're when you're in the middle of a titration. The first thing you need to do, because anytime you have stoichiometry, you've got to get to moles. So the first thing we want to do is calculate moles that we have of each that we've added together. And of course, moles is always going to be molarity times volume, right? So again, since it's a titration, it's more convenient instead of using liters to use milliliters. So we're just going to multiply milliliters times the molarity. So we find the moles of each of the substances. Then our mole table, remember a mole table is like an ice table, except that it's in moles instead of concentrations. So if we have 5 moles of KOH and 2 moles of HCl, this reaction, however much is there, will totally react. So since HCl is a limiting reactant, it's going to disappear first, and we're going to have some KOH left over. And you can really ignore the salt that's formed in a strong acid base because it doesn't affect the pH. I just had it there so you can see, help you visualize what's happening. So once you know what substance is left over and how much, we can easily find the pH. Since this is a base left over, we're going to be finding POH first, which is we need log of the concentration of OH. How do we get the concentration of OH? Okay, so remember, what is concentration? It's moles over liters, right? So 2.5 millimoles. Remember, if you keep it millimoles, but you have your volume in milliliters, you get molarity. So what is the milliliters? Well, at this point in the middle of a titration, your volume has changed, right? When you started titrating the KOH, you had 50 milliliters of KOH. But with every drop you add of the HCl, you're changing the volume and therefore the concentration of KOH. So in a titration, and again, I would make note of this, you need to add the total volume of everything that's been mixed together in the titration in order to find an accurate concentration. So we started with 50 milliliters of the KOH, and so far we've added 25 milliliters of the HCl. So our total volume at this point is 75 milliliters. So here's the concentration of the KOH left over, and POH therefore at 1.48. And remember, to find pH from POH, you just subtract the POH from 14. And we would expect this to be basic, right? We're starting with a very basic solution of KOH, and we're starting to neutralize it, but we haven't totally neutralized it. So keep your common sense in all this. You expect it to be basic. All right, so the much more complex titration is if you titrate a weak acid or a weak base. The first thing that I want to point out and to remember, because you'll see multiple choice questions about this on my test for sure, and more than likely on the final. The ACS tends to like these questions. So at the equivalence point, when you're titrating a weak acid, the pH is not equal to 7, it's greater than 7. At the equivalence point when you're titrating a weak base, the pH also is not 7. It is less than 7. What on earth is going on? Let's just look here. So here's acetic acid, which is a weak acid, and let's say that we titrate it with our strong base here. What are the products going to be? Well, at the equivalence point, as always in this chemical reaction, the original acid base are going to be gone, and you're going to be left with the salt and water. Now, the water portion is neutral, but this salt, different from NaCl, which was also neutral, you have the conjugate base from a weak acid. In other words, you have the acetate ion as a product that's left over. Okay? Since this comes from a weak acid, that means it can affect the pH. So we learned this in the last unit, so it's going to be critical in this unit that you understand. So if you need to go back and review, then go back and review pH of salts. All right, so this little bugger, the acetate ion, is what makes the pH greater than 7 at the equivalence point when titrating a weak acid. And this just kind of another way of saying the same thing. It is the salt, which is also the conjugate base from a weak acid, causes the pH to be greater than 7. So just another way of reiterating again, you can tell when I get to an important point because I repeat it 3 times. So again, if you're titrating a strong acid and a strong base, at the equivalence point, it's going to be neutral. If there's a weak acid involved, the pH will be greater than 7. If there is a weak base involved, the pH will be less than 7. Make sure you know this, please. So there are other ways that titration of a weak acid or weak base will differ from that of a strong acid or strong base, and the titration curve is an important difference. You should be able to recognize, given the shape of titration curves and the equivalence point, whether it's a strong acid slash base or a weak acid slash base. So in this drawing graph, the black line represents titration of a strong acid. It starts at a lower pH, which would make sense, right? A weak acid, given the concentrations are the same, is going to have a higher pH. It's going to be less acidic at the same concentrations than a strong one. And so the beginning pH is important, but more important than that, if you find the equivalence point of a weak acid versus a strong acid, the equivalence point of the strong acid is exactly 7. So remember how I told you to find the equivalence point, right? You take the halfway point of the big jump in pH. Now, let's look at the pH at the equivalence point for some weak acids on this graph, okay? So it's going to depend on the Ka for the weak acid, how weak of an acid it is, because remember, the weaker the acid is to begin with, the stronger the base its conjugate base is. So that's going to affect the pH at the equivalence point. So all of the remaining curves represent weak acids. And you would have to kind of see these individually to estimate their equivalence point. But you find the equivalence point in the same way. Okay, it's still the halfway point and the big jump in pH. But you can see that pH tends to vary, here between 7 and then just over 10. But in all cases, the pH at the equivalence point when titrating a weak acid is going to be greater than 7. My experience is almost all the time they're between 8 and 9. That's just the most common region that I've seen. Further complicating titration of a weak acid or weak base is that in the middle of the titration, we have what we call a buffer region. What does that mean? Well, if you remember what a buffer is, it's the roughly equal amounts of a weak acid or weak base and its conjugate pair. And so as we titrate a weak acid, and here's acetic acid, what do we form? Let's just look at that for a minute. So if we're titrating acetic acid, and I'll just use NaOH, what are the products that we're making? Of course, water is always one of them, and then the salt is the other. And so this salt, really, remember, it's going to exist as separate ions since these are aqueous solutions. So the salt is really a source of the conjugate base of acetic acid. So in the middle of a titration of a weak acid, or a weak base, it happens too, you've got the weak acid and its conjugate base both in significant proportions, and therefore you have created a buffer. And so that's why pH changes very gradually when you're titrating a weak acid or a weak base, okay, because you literally have a buffer. So you're not going to have as steep of a jump at the equivalence point as you do for a strong acid. And it's because of that buffer. And you will see as we go through the rest of this lecture that because we've created a buffer in the middle of titrating a weak acid or weak base, we're also going to use the Henderson-hasselbalch equation to figure out the pH when titrating a weak acid or weak base. Here are the different regions of a titration curve for a weak acid or weak base that we'll be doing calculations for. So again, I've kind of alluded to these, but we're going to start getting in a bit more detail. So typically you're asked to calculate the pH before a titration begins, which is kind of a ridiculous question. It's almost a trick question because they'll say, acetic acid is being titrated with sodium hydroxide. What is the pH at the beginning? So they didn't even have to tell you what they're titrating with, right? If it's the beginning of a titration, no sodium hydroxide has been added, and all you have is a weak acid. So it's just a weak acid ice table. So don't be tricked by that question, please. Then, as I mentioned on the last slide, all through the middle of the titration, you have a buffer, and so we'll be using Henderson hasselbalch to calculate pH. And then at the equivalence point, it's more complicated for a weak acid or weak base than it was for a strong one. And then, of course, if you overshoot the titration, you're going to have created excess base, and that's a different type of calculation. So kind of to give you a brief overview of the type of calculations to find pH at different stages in a titration of a weak acid. So in the very beginning, when you have a weak acid, which is going to call it HA, before you add any base, again, that is simply just an ice table for a weak acid. So don't be fooled by that. That's not even a titration problem. The instant you start adding titrant to it, you have the buffer. You have created the buffer region. And so this will be what most of your calculations will be, the buffer region. And so that'll be a two-step calculation. The first calculation will be a stoichiometric one, where you're just figuring out the moles of the weak acid that you have left, as well as the moles of its conjugate base that you've created from the titration. Once you know the moles of the conjugate pairs, you can then, in a step 2, use the Henderson-Hasselbalch formula to calculate pH. So let's work through some examples. We're going to titrate acetic acid. We know that's a weak acid, and if you didn't already know that, the fact that they gave you a Ka gives it away. And we're going to we're going to calculate the pH at different stages in the titration. At the beginning, okay, when no base has been added, and then at various increments. So I always try to keep in mind where the equivalence point is going to be. You can also calculate that, but check out the comparative molarities of the acid and base in the titration. It's always easier if they're equal. In these cases, they are. So that means since equal concentrations and the stoichiometry is 1-to-1, that since you start with 50 milliliters of the acid, the equivalence point is going to occur when you add the same volume of the base, right? So it's just kind of nice to know where you are in the titration. The halfway point would be when you add 25 milliliters, right? And so 51 milliliters is going to be past the equivalence point. Somebody overshot the titration. So anyway, let me erase this and let's go through each of those stages so you can see how it's done. All right, so the first one is going to be in the beginning. And I can't emphasize this enough that I see so many students tricked by this problem. The first step before titration, there's no base added, so don't try to do any chemical reaction. Just ignore the NaOH. It's simply a weak acid ice table, right? So remember how to dissociate a weak acid in water and your X values, okay? And so you're basically going to set up that Ka, right, 1.8 times 10 to the minus 5 is going to equal X squared over 0.10 minus X. It's okay to neglect X because Ka is small. Then you're going to solve for X. Remember, X is going to be concentration of hydronium ion, and then find the pH of that. It's that simple. Again, keep your common sense. It's an acid, so the pH you get should be less than 7. If it's not, you probably made a silly error someplace. All right, so now let's start doing the calculations you would need to do once you start adding the base. Remember what I said a couple slides ago. That's 2 calculations. The first one is going to be a mole table because you have to determine how much of the original weak acid you have left and how much of its conjugate base you've created. This is your buffer system, and you need that to use the Henderson-Hasselbalch. So setting up a mole table, you need to find moles or millimoles, whatever you're more comfortable with, of the initial moles of the acid. Of course, the conjugate base is 0 initially. And then find the moles of the base that you have added. So remember how we're finding moles, right? Moles is, well, we'll just do millimoles, equals the molarity times milliliters, right? So we know the molarity of the base we're titrating with, 0.10, and we're doing the problem when 10 milliliters has been added. Okay, so that tells us that we have exactly 1.0 millimoles of sodium hydroxide that have been added at this point. That's where this number comes from. All of the OH that's been added is going to react. It's the limiting reactant, right? And so we're going to subtract 1 mole from the original moles of acid. So we're going to have 4 millimoles of the acetic acid left over at this point in the titration. The OH will always be gone. It's all going to react. And we have created 1 millimole of the conjugate base product. So now we have our mole ratio of the buffer constituents, the conjugate pair, and we're going to plug these mole values into the Henderson-Hasselbalch equation. So as a reminder, here's the Henderson-Hasselbalch. And plugging in all the information, remember to put whatever is serving as the base, conjugate base goes on top. And also remember in the Henderson-Hasselbalch, you don't need concentrations, right? Because that's a ratio, units cancel. So you can either put the amounts in moles, which is much easier in a titration, or you could put concentration. And so notice what's happened to the pH. Once we start the titration, the pH has gone up. Remember it started at 2 something, which you would expect. You're adding base, you're neutralizing some of the acid, so you expect the pH to go up. So skipping now to the equivalence point, what do we have at the equivalence point? At the equivalence point, by definition, all of the reactant is gone. All of the original acid that you're titrating or base, whatever it is you're titrating, is gone. All you have at this point are the products. Okay? The water's not going to affect the pH. But remember, the conjugate base from a weak acid or the conjugate acid from a weak base is going to affect pH. So pH is not going to be 7 when you're titrating weak acid or weak base. And how do you find pH of a conjugate base? It is simply an ice table for a weak base. That's all you have left. All you have left is this weak base present. And so you're simply going to set up the ice table for this weak base in water. It's going to in part regenerate a bit of the original weak acid, but more importantly, that reaction is going to cause a little bit of excess production of hydroxide. So here it is, a little bit easier to visualize. This is the product at the equivalence point. And so it is a weak base problem. Now, since it is a base, we can't use Ka anymore. We're using the base, so we have to calculate Kb. So this gets very complex. The equivalence point from titrating a weak acid or weak base is the most rigorous type of problem in this unit because it has so many things to keep in mind. So Kw is Ka times Kb. Oops. All right, so Kb then is simply 1 times 10 to the minus 14 Kw divided by Ka. And so we will need that to use that in the ice table. So here's the ice table. Now, the initial concentration of the conjugate base can be a little tricky. Remember that it's not equal to the concentration of the acetic acid you started with because you've been titrating, you've been changing the volume, you've been increasing the volume with every drop of sodium hydroxide that you added during the titration. So whereas the moles of the conjugate base equal the moles of the original acetic acid, the concentration doesn't. The concentration has doubled. All right, so make note of this, make sure you understand that. So again, it's just a simple weak base ice table where you set the products equal to 0, you use X. It's okay to neglect X because the KB we got from the other page is very small. And remember that, here it is, so it's very small. Remember that X, since it's a weak base, is going to equal the concentration of hydroxide. So you have to find POH first and then convert that to pH by subtracting it from 14. So at the equivalence point, the pH is 8.72. And that's a real common pH for weak acids to have at their equivalence point. You may have to watch that a couple times, and you clearly need to practice it several times. Alrighty, so occasionally, this isn't as common of a problem, but occasionally you'll be asked to calculate the pH for a titration that has been overshot, where too much of the titrant has been added. So then, what do you have left at that point? So let's look at titrating a weak acid with NaOH. So we know that at the equivalence point, we have this present, right? All the reactants gone, and we worried about this guy. If you shoot past the equivalence point, all you've done is add excess OH minus. So compared to the OH minus you've added, A minus is weak. OH is strong. So if you shoot past the equivalence point, you can now ignore the conjugate base. Just say thank you very much. That makes it easier, no ice table. And all you need to do is find the concentration of the excess hydroxide. Only the excess, right? Because the original hydroxide that was used to neutralize is tied up. So let's do an example. What's the pH when 51 milliliters of sodium hydroxide has been added? Now, 50 milliliters was the equivalence point. So how much excess hydroxide have we added? We've only added 1 milliliter of excess hydroxide. And so we have to figure out what's the concentration of hydroxide that we just introduced to this solution by doing this. Mole table, anytime you do stoichiometric calculations in a titration, I think the mole table is most useful. It keeps you from making silly errors, okay? So we're just going to do the regular mole table we do for all titrations. Calculate the total moles of the weak acid you had to start with. Calculate the total moles of the hydroxide that you have added. Now, instead of OH being the limiting reactant, which is pretty much always the case in a titration, compare them now, right? The weak acid is now the limiting reactant. There's less of it. So all of the weak acid is going to be gone, just like any limiting reactant is going to run out first. And then how much of the hydroxide is left over? Well, that's one you can probably do in your head, but I still suggest a mole table, right? 0.1 millimole. All right, so we've got to convert this millimole to concentration in order to get POH. So we need to know the total volume at this point. Well, we started with 50, if you go back to the question, we started with 50 milliliters of the original weak acid. And we added 51 milliliters of the hydroxide. So our total volume at this point is 101 milliliters. So the molarity of the hydroxide at this overshot point of the titration, we can now calculate it and calculate the pH. It's 11. It's a really high pH. So the pH at the equivalence point was 8 something. And just from those few extra drops, well, actually 1 milliliter of extra hydroxide, the pH has shot up almost 3 points. One last point I want to make about titrating a weak acid or weak base. And if this lab is still done, you do this in the lab also. But remember the Henderson hasselbalch equation. Let me write that out for you. Do you remember what happens when the concentration of the conjugate base equals the concentration of the weak acid? When those two equal each other, then log of 1 is 0, and the Henderson-Hasselbalch simplifies to pH equals pKa. So doing a titration of a weak acid where you don't know the pKa, it's an excellent way to find the pKa. Okay, so where in the titration is this going to happen? Where in the titration are the concentration of the original weak acid going to equal the concentration of the conjugate base? When the titration is halfway done. So, and this is another misconception by students that I want to clear up for you. All right, so let's say we start with 1 mole of a weak acid. The end of the titration, remember, at the equivalence point, there's none of the weak acid left. Okay, so a lot of students want to pick the end of the titration. Don't do that. You want the halfway point. So at the halfway point, you're going to have 0.5 moles of the original left, right? And you will have generated 0.5 moles of the conjugate base. So it is the halfway point, again, where you're going to be able to find pH or pKa. It's going to equal the pH at that point. So how do you find the halfway point on a titration graph? So first you have to, let me move this up. First you have to find the equivalence point. And remember that's like halfway up where the pH jumps a lot. And sorry, I can't draw a little dot. So let's say that the equivalence point is 20 milliliters. The halfway point will be at 10. After 10 milliliters added. So once you find the amount of base added for the equivalence point, just divide it by 2, go to 10 milliliters, that's the halfway point, and find out the pH. pH is in the y-axis to remind you, right? And that's going to be pH, which will equal pKa at the halfway point. So that's just kind of a cool little thing that you need to know and will likely show up as a multiple choice. And finally, to end this PowerPoint, if a polyprotic acid is titrated, you will see an equivalence point for each of the acidic hydrogens. So you might be given a graph like this, for example, and asked, this is a diprotic acid or this is a triprotic acid? And they should have shown this as going up a little bit more. But there will be a hump for each acidic hydrogen. So, for example, for H2SO4, you would see 2 humps. And that's it. Okay? So just be able to identify a polyprotic acid titration. That's it for titrations. Practice a ton, please.